this session, we will discuss about order of enol contents in different carbonyl compounds or different compounds in which tautomerism is present. Okay, so already we have discussed about acetone and acetaldehyde. Acetone almost 100% keto form only stable, even for acetaldehyde also, for even phenol means it is 1 comma 3. Phenol means here I written in last class where is here double bond O, here double bond, here double bond. This is phenol only, because here hydrogens are present, here two hydrogens are present. What is the name of this compound? 1, 2, 3, 4 means 2 comma 4 diene, 2 comma 4 diene, and 1 one. 1 one. Here we can write cyclohex. Cyclohex 2 comma 4 diene 1 one. But here it is negligible. It is negligible because here after tautomerization, whenever this bond shifted here, it will come here, and this H plus ion which is released now accepted by O minus. So here these two are already present bonds. Here this is newly found bond. Here it becomes OH. This is phenol. Otherwise, what we can write? 1, 3, 5. Triene cyclohex 1 whole we can write. 1 whole. It is 100% quantity or content. Order of enol content means enol content. This is enol. Enol content is almost 100% here. Here enol, this is keto form. Keto form is negligible because of its aromatic nature. Because of its aromatic nature. Aromatic compounds are more stable compared to non-aromatic compounds. So here enol content is more. Like this we have many examples. Again, acetoacetic ester EAA. Their enol content is 7%. One more again, that is acetyl acetone. For acetyl acetone, almost enol content is 76%. So like that we have different other compounds. So here I am giving order of enol content in these keto forms. I am writing here keto forms only. Keto forms only I am writing, but you have to assume that enol content. See here, first I am writing CH3, C double bond O, CH3. For this enol content is very less. This is acetone. Enol content is less. That means what enol content of acetone is less means keto content is more. Means almost 100%. Then after ketone, we can write acetoacetic ester. CH3, C double bond O, CH2, then C double bond O, here O, C2H5. This is acetoacetic ester, otherwise ethyl acetoacetate. Ethyl means this one. Ethyl. Aceto means this one. This is acetate. Short form is EAA. Ethyl acetoacetate. Enol content is less. Then C6H5 here I am writing. C6H5 means benzene. There is phenyl ring. C6H5, C double bond O, here CH2, then C double bond O. That side I am writing ester only. O, C2H5. This is ethyl acetoacetate. This is here ethyl. Here this is benzoyl and this is acetate. Ethyl benzoyl acetate. So its enol content is more compared to ethyl acetoacetate because of here benzyl group. Otherwise, phenyl group. Phenyl group is having a minus I group. having a minus sign nature, minus inductive effect, so that it can accept electrons from this bond, so that on this carbon positive charge increases, therefore it can easily attract this hydrogen. So this, because of this phenyl ring, acidic nature of this hydrogen increases more and more, and because of this oxygen or this oxygen, ester oxygen, here there are two lone pair of electrons are present. There two lone pair of electrons are present. These lone pair of electrons and this pi electrons, these are in conjugation. Therefore, here it decreases positive charge on this carbon atom, so that acidic nature of this hydrogen decreases due to this, so that its enol content is somewhat more, but here both the methyl groups are present. Both the methyl groups are present. Methyl group means here hyperconjugation effect, and here also hyperconjugation effect is present, and here minus plus I effect, here also plus I effect is present, so that here its enol content decreases, because of here positive charge on this carbon atom decreases due to these methyl groups. Here, positive charge on this carbon atom or positive charge on this carbon atom when increases more and more, then electron withdrawing nature increases. When electron withdrawing nature increases, then this middle CH2, otherwise active methylene group is there. No, at this carbon, hydrogen can be easily eliminated as H plus ion. Here, electron withdrawing nature here increases more and more. Why? Because of this C6H5, because of this phenyl group. This phenyl group has minus I nature, and here as it is here resonance effect is present. Here resonance effect is stronger compared to hyperconjugation even. Therefore, it can decrease this positive charge on this C double bond O carbon atom. So because of that reason, here enol content of ethyl acetate is less than enol content of ethyl benzoyl acetate. Why means here positive charge increased by this phenyl group. Here only methyl group is present. The remaining is same. Here due to this benzoyl group, otherwise phenyl group, enol content increases. Then next compound I am giving here CH3, C double bond O, CH2, then C double bond O H. Its enol content is more compared to this one, compared to ethyl benzoyl acetate. This compound, what is the name of this compound? 1, 2, 3. We can write 3 oxo, because C double bond O, if you consider it as a substrate, we can write as oxo. So 1, 2, 3, 4. 3 oxo is butanol. 3-oxo-butanol. Here only hydrogen is present. Like ester group OC2H5 is not present. Here it has no plus I nature, no minus I nature, no hyperconjugation nature, like that, no resonance also. So that here this CH2 group can be easily participated in enol form. So its enol content is more. Then it's compared to this enol content of acetyl acetone, already I given this explanation. CH3, C double bond O, CH2, then C double bond O, CH3. This is acetyl acetone. Enol content is almost 76%. 76% I given. Then after here benzoyl group one side benzoyl like this, C6H5, C double bond O, then CH2, then C double bond O, here CH3. This it has, what is the name of this compound? Like this, it is benzoyl. Up to here it is benzoyl. Benzoyl acetone we can write. Benzoyl acetone. This is acetone. This part is acetone. Here because of its minus I nature, here its enol content is more. Then after next, lastly, both sides I am writing benzoyl. C6H5, C double bond O, CH2, C double bond O, here C6H5. This is benzoyl. This is benzoyl, and this is here also benzoyl is there. So we can say this is acetophenone. This total it is acetophenone. We can write like this, no? This is benzene ring C double bond. This is phenone. Here this is acetone. Acetophenone we can say. So that here we can write benzoyl. This part is over. Benzoyl. This side acetophenone. Benzoyl acetophenone. So this is the order of different compounds and their enol content it is. Enol content. Here acetone enol content is very less than ethyl acetoacetate, less than ethyl benzoyl acetate, less than 3-oxobutanol, less than acetyl acetone, less than benzoyl acetone, lastly benzoyl acetophenone. So all these compounds you have to remember. Here only thing is here two phenyl groups are present. Two phenyl groups have minus I nature because of more electron density. In phenyl group here 6 pi electrons are present. Because of these 6 pi electrons, this phenyl group comes under minus I group. Minus I group means all the electrons are moving toward this side, means on this carbon atom positive charge increases. So that this hydrogen can be easily eliminated as H plus ion. So whenever electron withdrawing nature is more, in that particular compound, electron withdrawing nature is more, that can be easily participated in enol form, and enol content of that compound should be more. So you have to remember this examination point of view. Among these they may give 3 or 4, and these 3 or 4 they throw into question and ask what is the order of enol content. Otherwise, what is the order of keto content? What is the order of keto content means acetone keto content is more. Here all these are keto forms. Remember, I written keto forms. But what heading I written? Order of enol content of these forms. If you write enol form of this, it has very less content, less quantity than this one, than this one. So here I written keto forms, but order is with respect to enol content. If they ask keto content, then what you have to write? Greater than sign. Acetone has more keto content than ethyl acetoacetate, has more keto content than ethyl benzoyl acetate, has more keto content than this one. Like that we can write. So as per the question, they are asking in the question with respect to enol content or keto content, we have to observe carefully, and we have to opt a particular option. So this is about order of enol content of different compounds. Then we have different tautomerisms. Different tautomerism. Even nitro compounds also show tautomerism. Nitro compounds, not only carbon compounds. In all these examples, what I can carbon and hydrogen or ketones or carbonyl compounds are mainly are present. C double bond O groups are present, or ester is present. So these are participated in which one? Tautomerism. Maybe it is 1, 3 triad system. Otherwise, 1, 2 diad system. It is only for HCN. These here different enol 1, 3 system. Here this hydrogen shifted from this atom to this atom, means here 1, 3 system it is. Otherwise, a triad system. We have different forms. 1, 3 migration, 1, 5 migration, 1, 7 migration also we have. So before that, I'll give some more examples related to which one different other compounds. Other compounds means here nitro compounds I'm taking first. In nitro compound, nitro means N double bond O is present. N double bond O. There nitrogen is more electronegative atom. It is multiple bonded with the other more electronegative atom, that is oxygen, and beside that there should be alpha carbon and also alpha hydrogen. So tautomerism in nitro compounds. Tautomerism in nitro compounds. See here nitro compounds means what? RNO2. R means any alkyl group. This alkyl group must contain minimum 1 hydrogen. That is nothing but acidic hydrogen. So here I am writing CH3 N double bond O, O. This is the methyl nitromethane. It is. It is the nitromethane. Nitromethane. Here, this is a nitroform. This is nitroform. Like ketoform, here it is a nitroform. Similar to that, here when this bond shifted to oxygen because of its more electronegativity, nitrogen gets positive charge. This positive charge is compensated by this carbon hydrogen through hyperconjugation effect, we can say. Here hydrogen, I am writing in this way. This hydrogen when shifted here there should be double bond formed between carbon and nitrogen. This hydrogen eliminated as H plus ion. That H plus ion now combines with is O minus. So these two are in equilibrium. Double bond here N, here O, H, then O. This is the acid form because this hydrogen is now acidic. The hydrogen which is directly attached to more electronegative oxygen can be easily eliminated, so that we can say it is acid form. Acid form means acid form. Acid form. This is nitro form. So in this way, we can expect tautomerism in nitro compounds, and even we can write nitroso-oxamino, nitroso compounds. In nitroso compounds, nitroso form we have and oxamino form. Nitroso compound means what? N double bond was just. See here, I am taking CH3. Here N double bond O. This is the nitrosomethane. Otherwise, nitrosoethane also we can write. Here instead of methyl group, here if you take 2, here CH3. So what is the name of this compound? It is nitroso. Nitroso means what? NO group. Nitro means NO2 group. So nitrosoethane it is. It is nitrosoethane, but it is nitroso form. Here also double bond O is there, and here beside this alpha carbon is present, and alpha carbon, alpha hydrogen is also present. So like this I am writing. Whenever this bond shifted here, oxygen get negative charge, nitrogen get positive charge. So to compensate this positiveness, these electrons shifted here. So here this hydrogen is eliminated as H plus ion because it is giving its electrons to this nitrogen. So that it is eliminated as H plus ion. So that H plus ion now combines with O minus because these electrons are shifted to oxygen now. Oxygen will take more electron density. So that negative charge it will take. This negatively charged oxygen now combines with H plus ion. And these two are in dynamic equilibrium now. CH3, then CH, here double bond. N, here O, H. This hydrogen shifted from here to here. See, 1, 2, 3. This is also 1, 3 migration. In this also we can expect which migration? 1, 3 migration. Hydrogen is migrated from one atom to third atom. 1, 3 migration in all these compounds. Here in nitro compound also same thing, and in nitrosoethane also same thing. 1, 3 migration. In this way also we can expect tautomerism in nitroso compounds or even nitro compounds. Then 1, 5 migration will take. 1, 5 migration means hydrogen is transferred from one atom to fifth atom. Here the best examples are salicylaldehyde, Salicylaldehyde is nothing but orthohydroxy benzaldehyde. So 1, 5 migration. 1, 5 migration. For this example is salicylaldehyde. Salicylaldehyde. What is salicylaldehyde? This one. Here double bond, here bond, here bond. Here OH. This is phenol. And here CH double bond O. This is aldehyde. So here among these two functional groups, aldehyde will take more priority. It is principal functional group. So that we can say it is benzaldehyde. At benzaldehyde, this is the first carbon, this is second carbon. 1, 2 relation, it is ortho. So that what we can say, orthohydroxy. O means ortho. Ortho hydroxy benzaldehyde. Orthohydroxy benzaldehyde. Here, see this bond, double bond is there. C H double bond O. These 5 electrons shifted to oxygen. So oxygen will take negative charge. So this carbon now gets positive charge because of these electrons are shifted to oxygen. So electron density decreases at this carbon atom. So to compensate this positiveness, these electrons shifted here. Then this carbon will take positiveness. So that these electrons shifted from here to here. So that hydrogen gives its electrons to this carbon, positive carbon, and eliminates as H plus ion. So the released H plus ion now combines with the O minus. So here we can write in this way. Here these are already present bonds. Here this is newly formed double bond. Here O. Then here this is newly formed double bond. Here C H. Then O. That O minus now accept hydrogen. This is 1 comma 5 migration. See here, this oxygen is first atom. 1, 2, 3, 4, 5. Here hydrogen shifted from one atom to fifth atom. So that we can say it is a 1 comma 5 migration. So common name of this compound is orthohydroxy salicylaldehyde, otherwise orthohydroxy benzaldehyde, otherwise 2-hydroxy benzaldehyde. So this is one example for 1 comma 5 migration. One more example is orthonitrophenol we can take. One more, this is one example. Second example is orthonitrophenol. Orthonitrophenol. See here. Orthonitrophenol. Here this is phenol. This is ortho position. Nitroso group means NO group. NO means between nitrogen and oxygen there should be double bond. Here also similar to this bond shifted to oxygen. Nitrogen will take negative charge, positive charge. This nitrogen positiveness compensated by this bond, and this carbon gets positive charge. This bond comes here, and hydrogen is eliminated as H plus ion. That H plus ion combines with O minus. Here double bond. Here there is a double bond O. Here double bond N. Here O H. So here also 1 comma 5 migration takes place. These two are the best examples for 1 comma 5 migration. These are more stabilized through intramolecular hydrogen bonding, we can say. See here also this hydrogen I am writing like this. So here this is partially positive charged hydrogen, here partially negative charged oxygen. So between these two we can expect intramolecular hydrogen bonding. Intramolecular hydrogen bonding, so that it is stabilized through intramolecular hydrogen bonding. So this also I am writing this hydrogen here. So positive charge hydrogen, here negative, partially negative charge oxygen. Between these two we can expect intramolecular hydrogen bonding. So here also this is intramolecular hydrogen bonding. So due to intramolecular hydrogen bonding, these two compounds, which forms enol forms are stabilized. So enol forms are stabilized through intramolecular hydrogen bonding or intramolecular hydrogen bonding. This is an example for 1 comma 5 migration or 1 comma 5 migration tautomerism. Then 1 comma 7 also we have. 1 comma 7 means here para hydroxy benzaldehyde we can say, same as this para nitrosophenols also we can take. In these two compounds we can expect 1 comma 7 migration. 1 comma 7 migration. So here taking one more example with respect to 1 comma 7 migration. But there the intramolecular hydrogen bonding we can't expect, because here there is a possibility for ortho compounds. For para compounds, intramolecular hydrogen bond we can't expect. So 1 comma 7 migration. Here example is para hydroxy benzoaldehyde. Benzoaldehyde. So we can write like this. Benzoaldehyde. Here I am writing OH. There is the benzoaldehyde we are saying now. C here double bond O. Here H I am writing this benzoaldehyde. Para position is 1, 4. Here OH group. So whenever this bond shifted, oxygen gets a negative charge. So this bond now shifted from here to here. Then this bond comes here. This resonance. Then this shifted from here to here. H removed as H plus ion. This H plus ion comes with this O minus. So here this is already present bond. Here double bond. Here C H single bond O, and this O now will take H plus ion. Here this bond shifted here. This bond shifted here, no? Then here double bond O. This is the enol form. This is the keto form. Which migration? 1, 7 migration. Why? Here this oxygen is, for example, first 1, 2, 3, 4, 5, 6, 7. This hydrogen shifted from 1, 2, 3, 4, 5, 6, 7. One atom to 7th atom. So that it is 1, 7 migration. Similarly, just now we have given example nitroso compound, no? same as that. There ortho nitroso hydrogen, here para nitrosophenol. So here the same way I am writing. Here double bonds. Here double bond. Here I am taking para nitroso. Here OH group I am writing. Here N double bond O. This para nitrosophenol. This bond is shifted here. Oxygen get negative charge. This bond is coming here towards nitrogen to compensate its positiveness, and this carbon gets positive charge now. It will compensate this positive. Here this carbon now gets positive charge, so that this bond shifted here and eliminated as H plus ion. That H plus ion combines with O minus. Here double bond O. Here double bond. Here double bond. Here double bond N. Then O H. This is a tautomerism with respect to 1, 7 migration. In some cyclic compounds and ring and chain tautomerism also we have. Ring chain tautomerism. One more important thing here is ring chain tautomerism. Particularly, you can observe this in biomolecules chapter. In biomolecules, we have glucose, straight chain glucose, and we have one more glucose, that is pyranose form, cyclic compound. There also we can expect a ring chain tautomerism. Here I am taking this compound as example. CH3, then C double bond O, CH2OH. C double bond O, CH2OH. So here 1, 2, 3, it is acetone only, but ole, acetonol, otherwise what we can say 1, 2, 3. It is propane 1 ole, 2 one. So for this we can write like this: CH3. I'm writing here C double bond O, here CH2, here CH2, then here OH. In this way I'm writing. So this chain, this is chain. Here, whenever this bond shifted here, so here this carbon is here. It contain alpha hydrogens, no, which is bonded to OH group. So here, among these two hydrogens, these hydrogens remains as, but here this bond shifted from here to here. Means this oxygen now gets positive charge, right? This carbon gets which charge? Positive charge. Oxygen gets negative charge. So here this is totally, otherwise here two lone pair of electrons are present. This lone pair of electrons shifted from here to here. So we can write in this way: CH3, then See here O minus, then here CH2, here oxygen. Between these two there is a formation of bond, and here hydrogen remains as with one electron pair with one positive charge. You know, oxygen is more electronegative atom. Being more electronegative atom, it will not accept positive charge, so that it can accept immediately this bond. So these bonded electrons are shifted to oxygen to compensate this positive charge and eliminates as H plus ion. This H plus ion now combines with the O minus. So here we can write like this, CH3, here OH, then CH2, then here oxygen. Like this there is a formation of ring. This is ring. Here I given mechanism how the bonds are delocalized. So this is ring and this is chain. So ring and chain tautomerism it is. Ring and chain tautomerism. So this compound and this compound we can write. These two are ring chain isomers. Which isomers? Ring chain tautomers. So here ring chain tautomerism also present. One more very important thing here is benzoquinone. So many times I've seen this question. Generally in examinations like NEET, otherwise in mains examinations they ask a question with respect to tautomerism. How they ask means they give 4 or 5 compounds in options, and they ask among the following which will not show tautomerism, which will show or which will exhibit tautomerism. Like these questions they may ask. So all these just now we are discussing now, all these can show tautomerism. Requirements already given. There must be one alpha hydrogen, and there must be multiple bonded atoms with more electronegativity. So they are the minimum conditions to fulfill tautomerism concept. So here some compounds like benzoquinone. So this example is important. Benzoquinone I am writing. Benzoquinone. Here even though alpha hydrogens are present, this benzoquinone show will not show tautomerism. Remember, will not show tautomerism. This is important. So benzoquinone means we can write like this. Here double bond O, here also double bond O. This is a benzoquinone. See here also one hydrogen is there. Here one hydrogen. Here one hydrogen. Here we can write one hydrogen. All these are alpha hydrogens. With respect to this double bond O, this carbon double bond O, this is alpha hydrogen. This is also alpha hydrogen. Here also, with respect to this double bond O, this is alpha hydrogen, this is also alpha hydrogen. Even though alpha hydrogens are present, but these are not acidic. They are not acidic hydrogens. They are not acidic hydrogens. Why these are not acidic hydrogens? Because these hydrogens are present on double bonded carbon atoms. Double bonded carbon atoms. See, these are present on double bonded. See, here also double bonded carbon, here also double bonded carbon atom. And one more thing here is whenever this bond shifted from here to here, oxygen gets negative charge and this carbon gets positive charge. And this positive charged carbon now compensated by two concept here. One is if this hydrogen is participated, we can say it is hyperconjugation. If this double bond is shifted, then we can say it is resonance. Already earlier we have discussed hyperconjugation is not more strengthened compared to which one? Resonance. Resonance is more prior, means we have to consider both hyperconjugation and resonance. Both are present in the same molecule, they are opposing each other. Then we have to consider resonance only. By using resonance concept we have to move furtherly, not hyperconjugation. So here this hydrogen is also ready to give its electrons, but through hyperconjugation. This double bond also produces its electrons to compensate this positive charge through resonance. So that we have to give more preference to resonance concept, so that these hydrogens are not participated. So that is the reason. So these hydrogens are present here. This is hydrogen. This also hydrogen. Here also hydrogens are present. But these hydrogens are not acidic. Why these hydrogens are not acidic? Because they are present on double bonded carbon atoms. And one more reason what we can say here, whenever this CH bond shifted here, that delocalization is related to hyperconjugation. And this pi electrons double bond electrons are present. No, this pi electrons when shifted here, that concept is from resonance. We have to consider resonance among these two, resonance concept and hyperconjugation. Both, if present in the same molecule, we have to consider resonance. Through resonance only, we can explain the property of this molecule. So that here it will not show tautomerism. Which compound? Benzophenone will not show tautomerism. Remaining compounds like this benzaldehyde I am taking. Here benzaldehyde, C double bond O H. This is carbonyl compound, but this is alpha carbon. Here no alpha hydrogens. No alpha hydrogen, otherwise no acidic hydrogen. Similarly, like this benzophenone, C double bond O. We can write like this. Here also this is alpha carbon, this is also alpha carbon. This is benzaldehyde, this is benzophenone. This also having no alpha hydrogen. Here also no alpha hydrogen, no acidic hydrogen. So that benzophenone or benzaldehyde, these will not show tautomerism because of no alpha hydrogens. Here no tautomerism. Remaining all compounds like acetophenone also. Acetophenone means here instead of this C double benzene ring, we have to write CH3. Minimum one alpha hydrogen is present, it can participate in tautomerism. So there are different examples related to tautomerism, which will show tautomerism, which will not show tautomerism, and order of enol content. Order of enol content. In which compound enol content is more, in which compound enol content is less. All this information is very important for examination point of view. So you have to remember this. And in next sessions, we'll discuss about one more important isomerism, that is ring chain isomerism, and one more thing is double bond equivalent. Otherwise, index number we will discuss in next class. By using this, that we can expect total number of structural isomers, means including chain, position, then functional isomerism and metamerism. All these structural isomerism we can expect in one compound by using index number. That concept in next class we'll discuss if possible. By next class we'll conclude total structural isomerism, and if time permits we'll start geometrical isomerism, otherwise optical isomerism in next classes. Up to that, stay home, stay safe. Thank you.